Hi there. We're going to look at section 3.8, functions. Now, functions have a new notation that some of you may not be used to, and therefore you think it's going to be difficult. But even though it's new, try not to make this harder than it is. Actually, using what we call function notation, which we're going to get into here today, it is actually a cleaner way of answering questions dealing with equations. So what we're going to do on this first page of the notes is we're going to look at what is a function and how do you know if it's a function or not, after we talk about what is a function. And then we're going to talk about domains and ranges on this first page. And then we're going to look at graphs. We're going to spend quite a bit of time on domain and range, and they will spend a lot of time on domain and range when you look at in your 1400 class. All right, so I'm going to try to make sure you understand domains and ranges so that when you do get to 1400, it won't be that difficult. Not domains mainly. You need to really have a solid understanding of how to find a domain. All right, so we'll start with this. I'm going to cover up part of this as we go through it. All right, so in this section, we will develop the notation of a function. And it's going to look a little different, and people have a hard time with it, but I think you'll get used to it. Like I say, it's a cleaner way of looking at an equation and answering questions dealing with an equation. In this section, we will develop the notion of a function. I think I said notation, but I like that too. Something that is very important concept for all of mathematics, especially upper level mathematics. We use functions in calculus. It has to be a function in order for you to find the derivative and find the integral. So, functions are important in your upper level math, whether it's business calc or whichever one you take. Let's see. In the simplest terms, a function is just a map between two sets, a set of input values and a set of output values. When a number is input or is inputted, the function will do some operations to that number and will spit out a possibly new number, its output. Now, here we're going to start with domain and range. And again, domain is pretty important. Range isn't too hard, but the range is done mainly with graphs. But let's go ahead. The set of all inputs and the set of all outputs to a function, they have special names. The set of input values, what you're putting in, and in math, when we relate this to math, the input is generally going to be the x's, is called the domain, while the set of all output values is called the range. Now, this will make more sense as we do some examples. So here, a few more definitions, and then we'll look at our examples. For a function, let me straighten it out a little bit. For a function, each input must correspond to exactly one output in order to be a function. Each member of the domain corresponds to exactly one member of the range. If there is more than one output for that one single input value, it is not a function. All right, let's look at these ideas and examples to try to solidify that. All right, so again, our arrow represents a function. So you're putting a 1 in and into the function, and out comes a 10. You put in a 2 and out comes a 6. You put in a 6 into the function and you get a 4 that comes out. If you put in a 9 into the function, out comes a 3. We're going to determine if it is a function or not first. Then we'll identify the domain, and then we'll identify the range. Looking at this, we have the 1 only goes to the 10. It doesn't go to anything else. So far, so good. It's a function. The 2 only goes to the 6. The 2 doesn't also go to the 4. All right. So because the 2 only goes to the 6, we're still a function. So I'm looking at these input values individually. The 6 maps or into the function, and you get a 4. And then only a 4. So far it's a function because the 6 doesn't go to anything else, just the 4. And then the 9. The 9 just goes to a 3. That's what we mean by this exactly 1. So the 9 only goes to the 3. Therefore, this is a function. Notice I spent all of my time determining if it was a function with this group right here. All right. This one has nothing to do if it's going to be a function or not. Just this group. This is the input group. This is also in our math class, it's called the domain. So this is the domain, and generally in our equations, these are the x's. It's what's going in. So the domain is what you start with, okay? And then what you get out is called the range. And in our equations, it's usually going to be the y's. So what goes in is the domain, and what comes out is the range. In order to determine if it's a function or not, we pay attention to the domain only. As long as the 1 only goes to the 10, nothing else. So right now, this is yes, this is a function. It's yes, a function. I could change it so that it's not a function. I could take any of these and map them to a different number as well. So let's do the 9. The 9 goes to the 3, so only the 3. If I put the 9 to the 6, the 9 goes to 2 different numbers, not exactly 1. It is no longer a function. This makes it a no right there. All right. Without that, it is a function because each of these only go to exactly 1 number over here. We don't care what number it is over here. We don't really care to determine if it's a function or not. So yes, it's a function until I do this with the 9. The 9 goes to a 3, and the 9 also goes to a 6. So it's no. All right. With this arrow, it makes it a no. Without it, it's a yes. All righty. Let's look at B. And sometimes if this is all new to you, you can always stop the video. You can try looking at B. You can see, is it a function? What's the domain? What's the range? And then start it up again. Okay, first off, we're going to determine if it's a function or not. So we're going to look at these as individuals and see that they only go to exactly 1 output. So the A just goes to 1. I don't care what it is, it just goes to 1. The D only goes to 1. The E only goes to 1. The N only goes to 1. And the X only goes to 1. Notice we don't care how many. You could only have 1 letter over here, and they all went to that 1 letter. As long as each of these only go to a single number or letter over here, we're good. So this is yes, it's a function. Yes, a function. Now we're going to look at what is the domain and what is the range. The domain is what goes in. So I'm just going to kind of circle it here. And I'm going to put domain. If you guys, when you're in Pearson, if it asks you for the domain, you'll have to list it. A, D, E, N, and X. And sometimes, oh, sorry about that. I need to get rid of those. Okay. Sometimes it likes you to put these little set notation, which is on your keyboard, or it might be on one of the buttons down below. And sometimes they'll put them in there for you. But this is what you would put in for Pearson. This is the domain. The range is what comes out. So these would be the range. And in Pearson, you would probably need to list them. B, F. A lot of times they don't care about the order. Sometimes they say, you know, in decreasing or increasing, but for the most part, order should be okay. So it is a function. Here's the domain, and here's the range. If I wanted to make this a no, one of these would have to go to another one. Like, let's say the N would have to go to the P as well as the R. Now it's a no. You know, probably should have dashed that. That's all right. Okay. Because now the N goes to two different, and they all must go to just one over here. All righty. Let's look at another one. Again, you can fast forward. You think, I've got this. I've got this. Okay, we've got car companies and we have the make of a car. So we've got Ford, makes the Edge, Chrysler, Town and Country, Chevrolet, we've got the Trax and the Equinox. Now, is this a function? And the answer would be no. And they probably will not have you find the domain and range if the answer is no. Just no. You're done. All right. Okay, if they do want you to, this would be the domain, and these would be the range. But it is not a function. The answer is no. Why? Because of this right here. The Chevrolet goes to the Trax, and the Chevrolet goes to the Equinox. So this would be a no. All right? Because this guy right here goes to two different of these over here. This range over here. All right, let's keep working on this same idea. Just don't make it harder than it is. You guys will be great. Okay, let's look at this next example. Determine whether each correspondence is a function. The correspondence that assigns each person his or her weight. So is that a function or not? Can John weigh 150 pounds and at the same time weigh 160 pounds? No, you can't. John weighs just 150. He can't do this. So each person only has one weight, all right, that day at that instant. So because each person has only one weight, the answer is yes, because each person has only one weight. I always try to think of a counterexample in doing these, something that doesn't work. And all right, the correspondence that assigns to the numbers -2, 0, 1, 2, each number's square. So we're going to assign -2. I want to make sure I read that right. 0, 1, and 2, each number square. Well, if you take a -2 and you square it, you get a +4. Now, I want to caution you, I'm writing small to keep out of the other one. I want to caution you in that when you square a negative on your calculator, you have to put it in parentheses. Otherwise, they would have given you a -4, which is the wrong answer. So again, we'll deal with this here later as well, but you do have to have parentheses when you square it. Okay, now when you square the 0, you get 0. When you square a 1, you get 1. 1 times 1 is 1. And when you square the 2, you get a 4. So each of these only goes to 1. See, the -2 just goes to the 4. The 0 just goes to 1 of these. 1 just goes to one of these, 1. And 2 just goes to a single number over here as well. The 2 doesn't go to the 1 and the 4. So yes, this is a function. Ready? Okay. Even though this occurs twice, that's all right. We don't care. We don't care with how many arrows go to these guys. We don't care. It's just coming from these, it can only go to one. All right, let's look at another example here, our last example before we start applying more of the algebra. The correspondence that assigns to a best-selling author the titles of the books written by that author. So you try to think of an author that may have more arrows coming from him than another. I'm thinking Jordan Peterson. Most people now know Jordan Peterson. Okay, Jordan Peterson, author. He wrote the 12 Rules of Life. 12 Rules of Life. I should have probably capitalized rules. Rules of Life. He also wrote Maps of Meaning. And then Beyond Order. Yeah. So, and again, so you see how Jordan Peterson has more than one arrow, you know, and Beyond Order. Beyond Order. Just abbreviate it. Beyond Order. I'll write it out. Okay, those are, I mean, he probably has others. Those are the only ones that I can think of. But anyway, so this idea is not a function because the author has different mappings to different books. All righty, so that is not a function. Okay, well, I hope that is kind of clears up what a function is. Now we're going to bring in more algebra. All right, so here, sorry, get it kind of set here. All right, a function is a correspondence between a set called the domain and a second set called the range. So we kind of talked about that on the last page, such that each member of the domain corresponds to exactly one member of the range. Okay, so let's look at some examples of graphing. The graphs on this page here are all functions. On the next page, we'll look at some graphs. How do you know, looking at a graph, if it's a function or not? But for right now, these are functions. So find the domain and range of each graphed, of each function graphed below. Well, just like I said earlier, the domain are the x's. All right, in our equations, the domain will always be the x's. What values of x are you putting in? And the y's are the range. What values are coming out of your function? So looking at this, if I wanted to find the domain, and I'll just use a D for domain. It's just a set of numbers. The first one, the first x is a -3. Okay, that's our first it's our first x value that was used. We also have a 1 that was used. Okay, for this point. This point, the x value was a 3. And this x point, the x value was a 4. So there's our domain. It's all the x's. So if I could actually go ahead and find the ordered pairs, -3, 1, 1, -2, 3, 0, and 4, 5. I could find the ordered pairs, and they may give you the ordered pairs and ask you for the domain. The domain are the x's. Just list them. -3, 1, 3, 4. The range are the y's. So our range is 1, -2, 0, and 5. Now, if for some reason, well, no, never mind, that won't work. Skip that thought. So here our domains are the x's. The range are the y's in these ordered pairs, in these points here. The domain are the x's, and I'll put that right here, and the range would be the y's. If you're given points. What if we look at B? What if we're given a graph here? Now we're going to talk about interval notation, and some of you may be familiar with interval notation. We'll look at set notation as well, which is what most people have used in the past, but interval notation, it's quicker and Pearson likes it. So we'll do both. Now I have infinite number of points between here, and that's what this graph represents. So again, to find the domain, I am going to look at the x's. We start with the furthest to the left, all right, because we read our graphs from left to right. The furthest left x is a -5. All right, that's the furthest to the left we go, because we're just going left to right here. The furthest left, the x's, is a -5. The furthest to the right that we go is 4. That's the furthest that we go to the right. So we go from a -5 to 4. What are the ways of writing this? First off, you could go a -5. This is set notation. The x's are greater than a -5 and less than 4. And then I like to read it as x's are between -5 and 4. All right, for your set notation. Interval notation. They're filled in dots. Better put the bar underneath them. Less than or equal to. So they include those because those are filled in circles. Interval notation, this means that it's included, okay, to 4. So -5 to 4, including the -5 and the 4. And again, I'm hoping that you've seen interval notation in your past math classes. Both of these are correct. Pearson will only count one of them right, depending upon which one they want. So you can either put in this one or this one. Now, the brackets mean that it's included, and the 4 means it's included. And let's see if I have an example. Yeah, later on, if it's not included, what symbol do we use? And we'll talk about that in the last example on this page. All righty. Okay, let's look at the range. I like to look at ranges with a graph. So most of the time when I ask you for the range, you'll have a graph. All right, the range. The range are the y's. So you, just like we went to the furthest left on the x's, to find the range, you'll go to the furthest down, because we want the furthest, the lowest, I guess you could say. And that happens to be the lowest graph is a -3. That's as low as the graph goes on the y-axis, is a -3. The highest the graph goes on the y-axis looks like a 5. Yeah. All right. So sometimes it's kind of hard, but yeah, a 5. Now here, how do you write that? Well, the y's, and you do have to use a y for the range. The y's are less than or equal to, or greater than, y's are greater than or equal to a -3 and less than or equal to 5. I like to read it, y's are between a -3 and 5. All right. How do I write that in interval notation? So we go to the lowest to the highest on the y-axis. Set notation, you're including the -3 to 5. That is your interval notation. You've got your set notation with an inequality symbols, and they'll show up on the bottom as a button. And then this would be interval notation. So again, interval notation. Yeah, I'm gonna run out of room. Okay. All righty. Let's look at another example. Here, we're going to find the domain. So we look at the x's. Now on the last one that we did, our graph stopped here and our graph stopped here. How do I know it stopped? It doesn't have arrows. The arrows indicate that it's going to keep going, which we don't have. So now let's look at this one right here. If we look at these X's and we look at these arrows, this arrow means that it's going to keep going in this direction and it's going to keep going in this direction. So there's no stopping point on the left. There's no stopping point on the right. So our domain, get it out in there. Our domain in set notation, one of your choices would be all real numbers. All real numbers. Okay. Now, how do you do that in interval notation? Because they don't have all real numbers. Interval notation, we go from a negative infinity to infinity. All right, no, I am not using brackets. And the reason I'm not using brackets is the brackets mean that it's included. Infinity is not a number. Infinity is a concept. It's a concept of getting larger and larger, or smaller and smaller. Because it's not an exact number, it cannot be equal to it. And that's what the brackets mean. It's equal to. Here, whenever you have infinity, you always use parentheses. So negative infinity to infinity with parentheses. That would be the domain interval notation. And it would be pretty obvious because this would be one of the choices if you're given, if they want it in a set notation. All right, let's look at the range on this guy. Well, not a lot of room, but I think I can do it. Range. We're going to look at the y's. Again, we have an arrow. See, this arrow is going down. It keeps going down, 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 which means that we don't have a bottom where we stop. It just keeps going down, and it just keeps going up as you go. It just keeps, the y values just keep going up, and the y values just keep going down. So this means all real numbers, or, common between them, negative infinity to infinity. You guys, you always have to have the negative infinity first in interval notation. This will always be first in interval notation. It does matter. All right, so we either go from the left to the right or the bottom to the top. All right, so it's always going to have the negative infinity first in your interval notation. Let's go to D. And I'm going through these slowly. You know, if you've got it, you can just, you know, fast forward, or you can keep watching. That's kind of the beauty of the online, is that I can kind of slow down, whereas in a classroom, sometimes you don't. But here, knowing that you can just kind of go forward on your own if you need to. Let's talk about the domain. All right, the domain on this one. So we look here, we want to know the furthest left. Well, you see this arrow? This arrow's going this way. So it's moving left. It's not moving left real quickly, but it is moving to the left and doesn't stop. This arrow, it's moving to the right and it doesn't stop. So that means the domain is all real numbers or negative infinity to infinity, or all real numbers. Okay. What about the range? Let's look at the range. We go to the bottom of the graph Notice over here, the bottom, because of this arrow, there never was one, but here, look, there is. Okay, what y value does this one start with? And this one starts with a -3. And again, the range is that y-axis. It's going to be this axis to determine your range. This axis determines your domain. So the bottom range is a -3. Does it include the -3? I'm just going to use interval notation because that's kind of what Pearson's going to be using for a while. So we're going to start with a -3, including the -3. That's the bottom number that we use, -3, and it's included. And we're going to go up from there. And because of these arrows are both going up, then we, it doesn't stop. It just keeps going higher and higher. And we express that as infinity with the parentheses always. Okay. What if that were upside down? Nope, I don't have one upside down. If this were, well, I'll do it after this one. I'll do an upside down one here. Okay, let's look at this one here just to see. All right, let's look at the domain. All right, I'm going to put it on the side. Notice it was kind of easy to write the domain and the range with interval notation. Now, this one, to tell you the truth, the set notation is a little bit easier with this one, but you'll see. Just one moment, please, just a second. Okay. Now, dog. Domain, the x's. Well, it looks like I've got this arrow, so it looks like it's going to the left. All right, my x's, you know, the corresponding x's, it just keeps going to the left. So we're going to go -infinity. But it stops here when x is a -3. So you have a -infinity to a -3, and then it stops. It's broken. And then I'm going to use a parentheses because the -3, it's the x coordinate. I'm looking at the x's only. The -3, that open circle means it's not included. Then we go on and we go from a -3. I'm going to -3. Now we start again. So we went from a -infinity to a -3. Then we're going to go from a -3, and it looks like it just keeps on going to infinity. Positive infinity. Now, Pearson may have you put a comma in between them. Generally, though, they use this symbol, a union symbol, but we're not going to get to that union symbol for a little bit. Maybe it's in chapter 8, so it might be the next unit that we do. I'll have to look. But this union symbol will show up on the bottom when you're typing in, and so you click on it. And what this means, it's over here, or it can be over here. It's kind of like an or. It includes both of these. Now, how would I write that using set notation? This is the interval notation for the domain. -infinity, we started clear over here on the left, and we had to stop at a -3, -3, and then we kept going. That arrow says we keep going, so we keep going to the right. Now, set notation, I'm just going to put a semicolon here. X's cannot equal -3. That's it. That's all you have to put. So it's all real numbers except x cannot equal a -3. You know, this is a little bit easier. This symbol would show up down below, and you would write x cannot equal a -3 in your set notation. Okay. All right. Yeah. it might look, I want to demonstrate a little bit. It might say the set of all x's such that, and they would put this, you would write this, and then they would have this bracket on the other side. I got to move me up a little bit. All righty. This is read the set of all x's such that, this line here means such that x's cannot equal a -3. Okay, now let's look at the domain, or excuse me, the range. Now our range are the y's. Let's look at the bottom y. So this arrow means it's dropping. It keeps dropping. All right, it doesn't have doesn't have an endpoint like our last parabola did. So it just keeps dropping. So we have a -infinity. But then it's coming up. All right, so we have a -infinity. It's just dropping forever down here. We come up, but at a -2, we have a stop. We have a break in our graph at a -2. So we have to stop at a -2 and not include it. Then we start again for this next section. We start at a -2, and because of this arrow, it just keeps going up, 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 up. So a -2 clear up to infinity, and we'll union it. Okay, there's our range. In set notation, I hope that makes sense. Our set notation would be y cannot equal a -2. But I really believe you're going to do a lot of interval notation. But just in case, you could have these two. Y does not equal a -2. Everything else, it can be. All y's are all, you have a -4. I mean, it just goes on down forever. And it goes up, except for the -2. It goes to the left. -3 is our break, and to the right. So there's your domain. I wanted to look at real quick a parabola that's upside down. Quickly. Now I'll just move this up here. And all right, let me sketch a graph. I'm the best sketcher. But if we had a parabola that's shaped like this, there we go. And we have this point right here. We're going to call this called the vertex, and we'll talk about that a lot, how to find it, fun things like that. So this is 2, 3. What is the domain? Now the domain, and we'll just do interval notation. The domain, now you see these arrows, eventually they go out. And so every x will be covered. So our domain is a -infinity to, and then even though it looks like it's not going to move out, they move out just slowly to +infinity. So the domain is a -infinity to a +infinity, and use the parentheses. What's the range? Sometimes people get this backwards. That's why I wanted to talk about it. Okay, the range is, you always do the bottom first, even though you really want to go to that 2, 3 first. You go to the bottom of the graph first. So here, the range, it's going down forever. So it's a -infinity is where you would actually start at and move up. So our range is a -infinity. Remember, -infinity always goes first in interval notation. -infinity is always first. And it stops at 3. Okay, so it goes up, 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 and it stops at 3. And it includes the 3. So there's our range. Domain, -infinity to infinity. The range goes from a -infinity, because we always know that -infinity goes first. -infinity up to the 3. You start at the bottom and you go up. You start at the left and you go to the right. Okay, great. Let's carry on with our next page. Now, I told you on the last page that they were all functions. But what we're going to do on this page is determine, looking at the graph, if it's a function or not. There is an easy test to determine based on a graph if we are looking at a function or not. It's called the vertical line test. The vertical line test, if it is possible to draw a vertical line anywhere that will cross the graph in more than one location, then the graph is not the graph of a function. So let's look. What does this mean? Vertical line test, it's really easy. Okay, that means if you were to pass, looking at these 4 examples, if you were to pass a vertical line anywhere, notice that it only touches in one spot each time I pass that vertical line. It only touched once. So yes, it's a function. What about here? Well, this one's kind of easy. If I pass it right through here, it touches in 2 places. So it's automatically a no. If I passed it here, it's a no. You just need one of these. You just need a 1 no, and it's a no. So this one is a no because it's touching twice. This X coordinate has 2 different Y's, and we can't have that. The X's can only have 1 Y. The domains can only have 1 Y. So here, this is a no. What about this next one? Well, let's see. Let's pass a bunch and see if we can make one touch twice. Doesn't look like it. They all touch once. Once, 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 once. So this is a yes. Okay. And here, it's pretty obvious. Anywhere, doesn't matter. You're going to touch twice. You're going to touch twice here. So this one is a no. So that's called the vertical line test. Pretty easy. Just pass it. If you can find one spot where it touches 2 or 3 or 4 times, it's a no. You just need one little spot, and then it's a no. All right. Now we're going to look at function notation. Now, function notation and equations. Again, new to some people. Function notation. I'm going to talk about it a little bit before we do some of these examples. All right, most of you are used to having an equation. Y equals, let's just make it really easy, X plus 2. All right, that's an equation. Well, what we could do is we could say, okay, if X equals 3, then Y equals what? Okay, I could ask you that. Well, you would put 3 in for the X, and you would find, okay, 3 plus 2 is 5. So Y is 5. But like I said, function notation is a little cleaner than this and a little bit quicker, even though it's new. So you may not like it at first. And it all deals with this Y right here. We're going to change it. We're not going to write the Y when we do function notation. We're going to change it to, you don't always have to use an F. You could use a G, H, and they will. F of X. Okay. It no longer means F times X. So don't say F times X, because that's not what it means. So we kind of changed the rules, because we always used to say when 2 variables are next to each other, then you multiply them. And now all of a sudden we're changing the rules. So if you wanted to multiply them now, you would have to put parentheses around both of them. And then you would multiply. But if there's no parentheses around the F, then it is read F of X. And this means that you're dealing with a function. So it would, if you were to graph the solutions, it would pass the vertical line test, either way, depending upon, the function, what the picture looks like of the answers. So it is a function. And everything over here are X's. So it's an equation in terms of X, and the equation is a function. Just by saying this, we've said a lot. the equation only has x's over here. Okay, that's not a z, that's a 2. So it only has x's. I cross my z's. It's in terms of x. So you can only have the variable x over here. If I made that a y, you could only have y's over here, or w's, you can only have w's over here. So this tells you the variable that's being used, and it tells you it's a function. All right. So knowing that, how can we clean up this question right here? I can ask this question given this notation like this, f of 3. This means to put 3 into the x and see what you get. So if I put 3 in for the x, I get 5. So this and this mean the same thing. All righty, so let's kind of repeat that. This is read f of x. It tells you that over here on the right, we only have x's, is our only variable. We can have numbers, but no other variable other than x. We know that it's a function. All right, so we know it's a function in terms of x. Now, you don't always have to use f. So let's say I have another one. Let's do another example. Let's say I have g of x equals x squared plus 2. And I want to know what g of 3 is. Okay, what is g of 3? Now notice I'm using of, I'm not going g times x. G times 3, it's read g of x is equal to x squared plus 2. What is g of 3? All right, and this means you put 3 in for the x, put 3 into this x, and see what it equals. So if you do that, I'll actually write it out, because for some of you it's totally new. 9, or just type it into your calculator and let your calculator do the PEMDAS for you. So g of 3 is equal to 11. Let's go back to our old notation. Let's translate this back into our older notation. What we did is instead of g of x, I can write y. And when you're graphing, a lot of times it's easier when they ask you to graph a function to change it back to a y. It means the same thing. And what I asked here was that if x equals 3, then y equals what? And you would put 3 in, square it, plus 2, you get 11. So this is what you have been doing, and this is what we will be doing. This means a y, and this tells us that over here we have x's, and that it is a function. That when I put in 3, I'm only going to get one answer. I'm not going to get another one. I'm only going to get one answer. If it's a function, I expect one answer, and I did get one answer. That one answer is 11. Okay. Now, we're going to talk a little bit about the notes that were given, now that we kind of have a general idea. Oops, let me move it down so we can all see. All right, function notation and equations. To quickly indicate which output corresponds to a specific input of a function, we use function notation, which is what we just talked about. For example, if we want to indicate that for an input of 3, the corresponding output is a -1, we use the expression, so you're putting in the 3 into the function, in for the x's, generally it's x's, that way it's easier to graph, but it doesn't have to be. We're going to put a 3 in for all the x's into the function, whatever it happened to be, and we're going to get a -1. Our last example, like the g of x, we put in a 3 and got an 11. They get a -1. So let's keep going. Most of the functions we deal with are described as equations because it's a math class, go figure. In this case, we will write f of x equals some equation. I had x plus 2 and x squared plus 2 as in the last ones. So you're going to have some equation over here. For example, f of x equals 2x plus 3 is a function. It's a function. It's got the function notation that takes the input, x, multiplies it by 2. So whatever x happens to be, you're going to multiply it by 2, and then you're going to add 3 to get the output, the range. All righty. So what you're putting in is the x is the domain, and then you put in the domain, and what comes out is the range. All right, in the above example, we want to know what happens when we input the number 4. You just plug x equals 4 into the equation, and this value would be called f of 4. That's how we read that, f of 4. So if we were to put 4 into the above equation, that's what this means, in for the x, any x. So no matter what x's you have over here, you could have like 2x squared plus 5x plus 3. All the x's become a 4. You would have 2 times 4 plus 3. And you get 8 plus 3. Oh, so we get 11. Perfect. So f of 4 equals 11. Great. The notation f of x is read aloud as f of x. It is important to note, that should be an E there, that it does not mean f times x. You know, it changed the rules on you. Sorry. Okay. Well, let's do some more equations. Find each indicated value. So we want f of 5. So that means we're going to put 5 into any x that appears over here. There's only one x that appears over here, but if there were more, you would put x into all of them, or 5 into all of them. So we're going to have 3 times 5 plus 2. I guess, you know, maybe don't make it harder than it is. It's just new. It's not hard. It's just new. 15 plus 2 is 17. So you could write f of 5 equals 17. Great. Oh, here we go. Now, g of a negative 2. What's g of a negative 2? G of a negative 2, you're going to put a negative 2 into this equation. Now, this equation has r's and not x's, and that's okay. This just tells you what variables you're going to find over here. You're only going to find r's. If there's an x in there, you've got an issue. All right, that never happens when we use this type of notation. It's a function in terms of r is how we read that. And so we put in a negative 2 into all our r's over here. 5 negative 2 squared plus 3 times, I'll just use parentheses. And I stated this a little earlier, make sure that with that negative 2 that you put it in parentheses before you square it, or it'll give you the wrong answer. You've got to have that in the parentheses if you're going to use your calculator. If not, if you're just going to go mentally with this is fine. 5 times 4 plus 3 times a negative 2. I'm going to have to go to the right. 20 plus a negative 6, 14. So g of a negative 2 is equal to 14. Again, this is our x. If we were to graph it, even though it's ours, pretend that we were going to graph this, this would be our x, and that would be our y value. So our ordered pair would be negative 2, 14. That's how you would graph that. All right. Like on this one, this is a good point, and I'm glad I thought about that, is that what's going in, these numbers that are going in are always going to be your domain. So if we were to graph this, it would be the coordinate 5, that's the x that went in, and the y came out. Okay. So this is the 5/17. What's going in, what's coming out. And when we do start graphing, you can always take this and change it back to a y in order to graph it. And that might help some of you. So, perfect. We have another one. Ooh. Find h of 4 for the function. So we do have a function. It's got the function notation. Only x's appear over here, and it is a function, but there are no x's. So what does that mean? If you were to put a 4 in, then I'll write it as an ordered pair. If you put in a 4, you still get 7. If you put in h of 5, it doesn't change. Your y values are always 7 because there's no variable to put these into. So this one right here is also 7. So you'd have the 0.57. Remember, this is y equals 7, is another way of writing that. So if there's no variable, it means that that y coordinate always stays the same, no matter what the x becomes. So if I had h of 6, you're going to get 7. So I would have the 0.67. Connecting them, it forms a horizontal line with a slope of 0. Kind of review that idea. Okay, so you always just get a 7 every time, no matter what x you put in. For whether or not you put in a 6, you always get a 7 out. All right, perfect. There's so much in this section. This is a long video. I guess you guys can pause it and take a break. Another one. Oh, they're going to get a little bit tougher. So, yeah, that's all right. All right, f of a plus 1 for this function. All right, this means you're going to put a in for the x's. This is what you always put in for the variable. And then we're going to add 1 to it. So we're going to put in, usually we were putting in numbers in. Now we're going to put a variable in. So f of a, I'm going to put an a here. And then I'm going to add 1 to that. So I put an a into here. That's what I got. And then I add 1 to that answer. So I'm going to add 1. So this is 3a plus 2 plus 1. Pearson would count this wrong. Sorry about that. So this right here becomes 3a plus 3. Let's review that idea. I'm going to find this by putting a in for the variable. So when I do that, I get 3a plus 2. That's what this is. 3a plus 2, and then you add 1 to that. And this would be the answer. They do say simplify, so you do need to simplify. All right, maybe we have another one here. And D and E are totally different. Here you find f of a first, and then you add 1. Here, rather than substituting in an a into the function and getting 3a plus 2, we're going to substitute this in for the x right here. So this is what you always replace your x with. Normally, we were doing a number like 3. We were putting 3 in for the x, or 4 in for the x. Now we're going to put a plus 1 in for the x. And then we still have the plus 2. Got to have that. And now you simplify that. Going back to this one, I just put the A, it's in the parentheses. This I put in an A, and I got this, and then I added 1. But now the 1 is included in the substitution. So I'm going to put this in for the X, and then you put that, you have that added to there. That's part of the function. That's always going to be a part of this, the +2. So we clean it up by using the distributive property. Then we have our +2. The 2 is not in the parentheses, so you don't multiply it. And then we get 3a plus 5 as our answer. That's what this is equal to, 3a plus 5. And this was 3a plus 3. So it doesn't matter where that 1 is. Okay. Let's do, oh, yeah. Okay, this isn't too bad. Let's do another one like that. So we have our function here. We've only got x's. And we're going to, instead of the x's, we're going to put an a in for the x's. So we're going to do that first. So I'm going to put an a in for this x. And that's what I get, 3a minus 6. And then I'm going to add 2. And we clean it up by combining like terms. And that's what your f of a plus 2 is equal to. That right there. It's a little different, but I think you guys will be fine. All right. And again, this is, it's just stating in a different language what we've been doing. What is the output that corresponds to an input of 5? In other words, what's f of 5 equal to? So we put in 5. 3 times 5 minus 7. So instead of a variable, now we're using a number, which you guys probably like better. 15 minus 7. And so you're going to come up with 8. Okay. 8 is your answer. F of 5 equals 8. That's the output. What is the input that corresponds to an output of 5? Okay, now we're going to have to do a little bit of solving. We haven't talked about this. So we have been taking, I've been saying like, what is f of 5? Okay, now I want to know what x will equal 5. Okay, that's how we could say that. When does the function, the whole function, equal 5? So there's a difference between this and this. Here you put it in for the x. These are easier. Here you take the function and set it equal to 5 when you want the output to be 5. So you have 3x. When does the function equal 5? That's what that is asking there. A little bit different. You have to solve the equation. You have to solve this 2-step equation. You have to add 7. And then divide by 3. So f of 4 equals 5. So they wanted the 4. So what is the input? What is the x that gives you a 5? And you just set the function equal to that output and solve it. A lot of times they write it like this, in function notation. Okay, wow. Determine the domain. Piecewise linear. Okay, we'll press on. Okay, for each equation, determine the domain. So we were determining the domain if it was given a graph. and you just looked at the x's. Now, when you're given an equation for right now, I'm not going to ask you for the range. I just want to know what is the domain. That's kind of what we're interested in the 1400 in your calculus classes is the domain. All right, what you ask yourself a question. What x's can I not put in? Well, if it's just a basic equation like this, there's nothing I cannot put in and have it be undefined. So the only time you're going to have to worry about limiting your domain is if you have a fraction. I'll just use this one. Here, you're going to have to do some math because you have an x down in the denominator. Here and here, you can put in anything. So the domain is a negative infinity to infinity. If you were to graph that, okay, if you were to graph that, it would be a straight line. And so you can always graph it and look at it if you want to, if it's pretty easy to graph. You would go to 5, 1, 2, 3, 4, 5, up 3, and over 1. And so here it's pretty easy to see that there's no breaks. The x's, negative infinity to infinity. Or you can ask yourself, is there a number I cannot put in and you're going to get an error on your calculator? Well, you can take 3 times any number. Fraction, it doesn't matter. Radical, you could put in 0, any negative, it doesn't matter, and times it by 3. You don't get an error on your calculator. So this is the domain is a negative infinity to infinity. The same with this absolute value of x, and we'll be dealing with absolute values here. Chapter 8. Yeah, I think it's absolute values. And so here, again, there's no fraction. The only time you have to think, uh-oh, I may have to limit my domain from a negative infinity to infinity is 2 times when you have a fraction or a radical in the equation. Otherwise, it should be this. And when I say a fraction, I mean that the x is in the denominator, not that you have, see, if I had f of x or whatever variable I want to use, f of x is equal to 2/3 x plus x squared over 5. That has fractions, but there are numbers down in the denominator, and those can never become 0 by themselves unless there's a variable. So this domain is a negative infinity to infinity. So as long as you have a polynomial or you like these absolute values, your domain is a negative infinity to infinity. You can put in anything and your calculator will be fine. But if you have a fraction, then we know in mathematics that you cannot have a 0 in the denominator. When you're looking at domains, you look at the denominator only. We're not interested in the numerator up here. You only look at the denominator. The denominator for the domain, maybe that'll help. But 2x minus 6 cannot equal 0. Right? And this is one of our limits of our domain. And I don't know, I don't think I did a radical. No. So for right now, that's all you have to remember. The denominator for the domain cannot be 0. And you solve this. Add 6. You add 6 to both sides. Divide by 3, or excuse me, 2. I just said the answer. X cannot equal 3. And that's your domain. X cannot be 3. How do you write that in interval notation? Negative infinity to 3, because you have a break at 3. You can't include the 3 unioned with 3 to infinity. Okay, it would have a break, and we kind of did those with those graphs. All right, so otherwise, negative infinity to infinity until you come to a fraction. And hopefully they'll accept that answer right there. Okay. All right. Let's carry on. Let's push through 3.8. Oh, I like this one. All right. For the graph below, now we're going to given a graph and we want to find f of 2 rather than an equation. If we had an equation, we would put 2 in for the x's or whatever variable and see what it equals. Well, what if we're just given a graph? Okay. Find f of 2. So that number is always the x, and they're asking you for the y. So you go to 2 on the x, you go up, the answer is 5. So if you put in 2, you get 5. So f of 2 equals 5. Let's do another one. What is f of a negative 5? I'm just kind of looking at the graph. So you go to a negative 5, and the y value is 2. So you have the point 2, 2, 5, and the point negative 5, 2 on the graph. Now let's go to B, the domain. What is the domain? The domain are the x's, and it looks like, let's see, this is A, +1, B. The domain starts at a negative 5, the furthest to the left, and it includes negative 5 to a 2. That's the last x that is part of the graph. And it includes it because it's a filled-in circle. Okay, any values of x for which f of x is equal to 1. So now, rather than giving you the x of 2, now you're given the y value. What x's give you a y value of 1? Well, there's this one, and that is not on the graph exactly, but I guess we'll just have to estimate on this. So what x's give you a 1? Well, the 1 gives you a 1. We'll say that's 1, even though it could be like 0.75 or something like that. We'll call it f of 1 gives you a 1 y value. And it looks like, I guess we'll go for negative 4.5. F of a negative 4.5 gives you a 1 as well. So that has a y of 1, and that has a y of 1. So 1 and a negative 4.5 are the two x values that give you y as 1. Okay. All right. Perfect. Let's go to our next section. All right, so we have the domain of a function. The domain of a function is the set of all possible inputs to the function. So if the correspondence is listed in a table or list, so I guess we're just reviewing domains. So if the correspondence is listed in a table or list, then the domain is the set of things in the first column. Okay, that's kind of what we did at the beginning. All right, that first page. If the function is described by a graph, then the domain is the set of all x values that cover that graph from the left to the right. If the function is described by an equation, then the domain is the set of all numbers that you are allowed to plug in. So for right now, it's negative infinity to infinity unless you have an x in the denominator. And then you have to set that denominator equal to 0. Otherwise, it's negative infinity to infinity. And if the function is an application problem, the domain is the set of all numbers that make sense in the context of the problem. Like if area cannot be negative, a length and width cannot be negative. So your domain would be from 0, because even if it's 0, you won't have a length or a width, or maybe distance is 0, time is 0. You don't have a lot of negatives in the application problems. So the domain would be from 0 to whatever, and we'll look at those later. Okay, the last thing we're going to look at is what's called a piecewise defined function. This is an example, and it looks harder than it is. These functions that have different equations for different parts of their domain. To evaluate a piecewise function at an input, say, of x equals a, you first need to figure out which piece of the function x equals a falls under. So here's an example. We're given this function is equal to 2x if you're putting in a number that's less than 3. You'll use this, x plus 1, if you're putting in a number that's greater than or equal to 3. Let's look at negative 10. Now, you go to negative 10 and you see which one of these it fits. Is a negative 10 less than 3, or is a negative 10 greater than or equal to 3? Well, we know that a negative 10 is less than 3, so we put the negative 10 in right there. We use that part, the 2x part. So our answer is a negative 20. All right, let's look at the B. 3. Where does 3 fall? Is 3 less than 3, or is 3 greater than or equal to 3? It's this one, right? It fits this one. So we're going to put 3 in here. I meant to write x plus 1. 3 plus 1. You get 4. So this determines which one of these you use. 6. Is 6 less than 3? Or is 6 greater than or equal to 3? Well, 6 is greater than or equal to 3, so you put the 6 into this one, not this one. 6 plus 1. All right, so it's not too bad. I don't know if there's another example. Yes. I've got this one here. We have 3 of them in this piecewise function. It's not any more difficult. You take a negative 4 and you see which one negative 4 fits. Is negative 4 less than 2? Or is a negative 4 in between 2 and 4? Or is a negative 4 greater than or equal to 4? A negative 4 fits this one. It's less than 2. So you put a negative 4 into this part, because that's the one it fits. So 2, negative 4 squared minus 3. 2 negative 4 is squared is a positive 16. So 32 minus 3, you get 29. X is a 29. Awesome. I'm going to put a piece of paper underneath this. Now you do the 2. Which of the 3 would I use? Focus. All right. So you use this part over here. Is 2 less than 2? Is 2 between 2 and 4? But see this bar? If it's equal to 2, then you would use this one. So it is going to fit this one because 2 is not bigger than 4. So here, this is all x's between 2 and 4, including the 2 because of the bar under the 2, but not including the 4. There's no bar. So we're going to put the 2, because it fits this, into x squared. So we come up with 2 squared, which is 4. Great. Let's do 3. Where does the 3 fit? Is 3 less than 2? Nope. Is 3 between 2 and 4? Yeah, it is. And we know that 3 is not bigger than 4. So 3 is this one, so we put it into the x squared. Awesome. Let's do the next one, D. Hopefully, oh, I'm sorry. I guess I can't move that up. We'll just keep it down like this. 4. I want to make sure that it's focused for you. Sometimes it. All right, so now we're going to put in 4. We go over here to the right. Where does 4 fit? Well, it's not less than 2. And 4, you see, it doesn't have the bar here. So we can't use 4 here. We use it here with the bar. So we're going to use this one because 4 is greater than or equal to 4. So we're going to put it into this one right here. Not equal 7. So we have 20 minus 7 or 13. All right. Oh, we have one more. 8. So where does 8 fall over here? It's not less than 2. 8 is not between 2 and 4, but 8 is larger than 4. So we're going to use this one, 5x minus 7. 5 times 8 minus 7. So we get 40 minus 7, 33. All right. Awesome. I hope that makes sense with these piecewise. Okay, last one. I'm sorry, this has been kind of a marathon, but 3.8 has a lot of important information for your future math classes. So pause it if you need to. Example, the cost in dollars of a one-day truck rental is given by C of D equals 0.3D. This just tells you it's a function. It's a cost function that tells you the cost of things. And D is the only variable we've got here, where D is the number of miles. So we have 0.3D plus 20, where D is the number of miles driven. This model is of the form y equals mx plus b. It's linear because it fits this model here. What do the m and b signify? All right, well, the m is, okay, well, here, let's talk about the b first, this 20. What does that mean? It means that you have a basic charge of 20 before you've driven any miles at all. I like to think of it even easier is with a membership to a gym. A lot of times you have just a basic, like $40 to join the Y here, and then so much per month. So this right here is just a basic cost. Before you go anywhere, you're going to pay 20 bucks. So that's what that represents. B is the cost without any miles. And they would have multiple choice. Cost without any miles, or the cost before driving off the lot, okay, would be the B. Now the slope, the 0.3 is going to be the cost per mile. All right. So the M is the slope. And you need to remember that the slope is the Y. It's the rise over the run, which is the difference in the Y. So it has the Y units because you use the Y's to find this. The run is found using the X, so that it has X units on it. Those are the units that you use. The Y is the cost. So this is the money. So this is the cost per the X units. That's our D here, is the miles. So it's the cost per mile. So you can look at the units to determine what that slope is. It's the Y, it'll be this over the units on the X in that spot. So it's the cost per mile. And the 20 is just like an initiation fee. You just got to pay it. Okay, we're done. And that was a marathon. Sorry about that. And I hope that that helps. And again, if you have any other questions, please let me know. And I can Zoom with you or go through something again. All right. Thanks for hanging in there. Bye-bye.